Because these terms are vital for comprehending the characteristics of a reservoir and the primary and secondary drives used to produce oil from these reservoirs, let's review these 12 terms quickly. 1. A fluid is defined as a substance that takes the shape of its container. Water, oil, and gas are typical fluids contained in a reservoir. Number 2. To help us calculate the original oil in place, we figure the density of the hydrocarbon fluids. For that, we use API gravity. Always stated in degrees, API gravity is figured by comparing the density of oil with the density of water, which is pegged at 1. Number 3. Solution gas is liquefied gas that converts back to gas when pressure is lowered. 4. Critical saturation is the point where the percentage of oil in the fluid is high enough to make a continuous medium, allowing the oil to flow. 5. Bubble point pressure is the exact pressure where solution gas is in equilibrium with gas. 6. The gas cap is the gas that sits at the top of a trapped reservoir after bubble point pressure in the reservoir has been reached. 7. Viscosity, or mu, measures the resistance of flow rate of a fluid because water and different types of oil flow at different rates. 8. Associated gas is found with black oil. Non-associated gas is found by itself without the presence of black oil. 9. Condensate is gas in the reservoir that converts to a liquid at surface atmospheric conditions, like steam on a mirror. 10. Formation volume factor, or beta, measures the shrinkage of the volume of the liquid as it moves from the reservoir to the surface. 11. The gas-oil ratio, or GOR, measures the ratio of the volume of gas, SCF, to the volume of oil, STB. 12. The recovery factor, or RF, measures the percentage of oil in the reservoir that can be expected to be produced or recovered from a reservoir with current technology. Please become familiar with these reservoir definitions. As I said earlier, we'll need them to explain the reservoir's fluid systems and their characteristics in the reservoir. Now, it's time to turn our attention to different types of fluid systems in the reservoir. Here, we will examine the hydrocarbon classifications of 7 types of fluid systems. These classifications are based on the reservoir's mixtures of heaviest and lightest hydrocarbons. We'll start with the heaviest hydrocarbon fluid. It is called bitumen. Now, using what we learned in the definition section, let's examine the characteristics of bitumen. What do we see in slide 1? Looking at its API gravity, we notice that it is very low. Remember that the API gravity for water is 10 degrees, so if a fluid has an API gravity of less than 10 degrees, we call it bitumen. Since bitumen is heavier than water, it will sink. In fact, bitumen is the only hydrocarbon that will not float in water. We also see that bitumen's viscosity, or mu, is very high. This means that its flow rate is very resistive and probably won't flow without heat or other chemicals being applied. Both beta at 1 and RS at 0 indicate there is no solution gas. Bitumen, as you might guess, is used mostly in highway construction. In slide 2, we have the classification for tar, or heavy oil. Its API gravity is greater than water, so it will float. Beta shows that there is some shrinkage, and the RS shows that some gas is released at the surface. Slide 3 shows the classification of low shrinkage oils, or black oils. As you can see, the API gravity is getting higher and the viscosity is getting lower. More lighter hydrocarbons are in the mixture. Slide 4 shows high shrinkage oils or volatile oil. As the word volatile implies, this substance can easily change into gas, so its shrinkage is higher and its RS is also higher. A large volume of gas is usually found in volatile oils. Slide 5 shows the classification of retrograde condensate. In the reservoir, condensates are gaseous, but the gas liquefies and the condensates drop out at surface temperatures. In slide 6, wet gas is in a gaseous state in the reservoir, but some condensate, which may include water, will form at the surface. Slide 7 represents the classification of dry gas. Made up mostly of methane, dry gas produces no condensate. Notice here that there are no numbers for API gravity nor mu. API gravity approaches infinity and mu approaches 0. Because there are no liquids, beta and RS are meaningless. Now that we are familiar with some basic scientific classifications of fluids in the reservoir, let's now turn our attention to what is known as recovery. In production, recovery is the process of bringing to the surface as much hydrocarbons as good engineering allows. To maximize a reservoir's yield, different stages of recoveries are utilized at different times in a reservoir's production cycle to maximize this recovery. Currently, these recoveries can produce approximately 30% to 70% of a reservoir's hydrocarbons. There are 3 stages. The first is called primary recovery. The second stage is called secondary recovery, and the third is tertiary recovery. Secondary and tertiary recovery methods are considered additional recovery processes and are also referred to as enhanced oil recovery, or EOR. Let me describe the recovery methods in more detail. The first stage is called primary recovery. It relies on the energy naturally found in the reservoir. Next is secondary recovery. In this process, various types of man-made energy are added to the reservoir after the reservoir's own natural energy used in primary recovery is used up or depleted. Third is tertiary recovery. Tertiary recovery is the continuation of using various types of man-made energy. To be tertiary, however, another type of energy not used in secondary recovery is used. Secondary or tertiary recovery processes are often referred to as pressure maintenance or enhanced oil recovery. In either primary or EOR recovery drives, a source of energy is required to push the oil to the surface. In primary recovery, the energy is supplied by naturally occurring forces that come from within the earth and are referred to as natural energy. There are 5 major sources of natural energy. They are solution gas drive, water drive, gas cap drive, gravity drainage, and compaction drive. Let me explain. If you remember from our definitions, solution gas is liquid under pressure. When the pressure is released, the volatile gas rushes upward and outward, carrying the oil with it. All of the energy is supplied naturally. Thus, it is referred to as a natural source of energy. Measured in psi, or pressure per square inch, solution gas is the most common primary drive mechanism and is probably used in over 1/3 of all reservoirs throughout the world. The recovery factor for solution gas drives is from 5 to 30% with an average of 15 to 17% RF. The energy in a solution gas drive usually is managed in 4 phases. To better illustrate, let's look at the 4 phases of a solution gas drive. In phase 1, the reservoir pressure rapidly decreases linearly to the bubble point pressure. As you can see from this illustration, pressure starts out as a straight line until it hits the bubble point pressure when bubbles are released from the solution gas. Above this bubble point pressure, there are no bubbles. It's all pure liquid. Phase 2 is when the solution GOR falls below the initial GOR for a period of time. This is because some of the fluid in the solution gas is released into the reservoir as gas forming a gas cap. This trapped gas is prevented from being produced along with the rest of the solution gas as it is pushed to the surface. The gas remaining in the solution gas is the only gas produced, thereby causing this dip. At the point where the reservoir GOR stops falling and once again climbs above the original GOR is when Phase 2 ends. In Phase 3, critical gas saturation is reached and free gas is produced along with the oil and its remaining solution gas. Gas expansion from the continuing pressure drop is the main drive mechanism, and it pushes out the oil. In the later stage of Phase 3, the pressure drops rapidly because of the high gas production rate. This means that the reservoir is producing less oil. When the GOR reaches a maximum value, we state that Phase 3 has ended. In Phase 4, the producing GOR turns downward on the graph. The remaining oil has been depleted of its solution gas. It is at this point the production declines to its economic limit. Since there is very limited oil production with low pressure, this well will most likely be abandoned. As you can see in these 4 stages of a solution gas drive, oil production, reservoir pressure, and the gas-oil ratio all show characteristic changes that can be used to predict the next phase so that the reservoir can be efficiently managed. Because the recovery factor in the reservoir for a solution gas drive is usually between 15 to 17%, as I mentioned earlier, solution gas drive reservoirs usually need a secondary recovery method. Being able to anticipate the different phases helps the engineer decide on when to begin preparations for a secondary recovery.